Hello again. So last time we were talking about points in general position, and I stated the following theorem. Theorem 1.1. So this says if we let V and W be vector spaces of the same of dimension n plus 1, so they're projective spaces are of dimension n, and we let P0 up to Pn plus 1 and Q0 up to Qn plus 1 be sets of points in general position in the projective spaces P of V and P of W, respectively. So then the conclusion is that then there exists a unique projective transformation tutor going from P of V into P of W with tutor of Pi is Qi, but I is 0 up to n plus 1. Okay, so and the first thing we're going to do today is to prove this. So it's a geometric statement about things happening in projective spaces, but as usual we're going to lift up to the vector spaces V and W and then do linear algebra there. So the proof, well, so let's first choose V0 to Vn plus 1 in V and well, so representing the P0 to Pn plus 1 and W0 to Wn plus 1 in W, representing Q0 up to Qn plus 1. Actually, let's not do that yet. So then the first n plus 1 of them, V0 up to Vn, are linearly independent, as the definition of points in general position means that any n plus 1 of the n plus 2 points don't lie in a hyperplane, and upstairs in V any n plus 1 of the n plus 2 points are linearly independent, so I've missed out the Vn plus 1 there. So that's true as P0 to Pn plus 1 are in general position. So we have n plus 1 linearly independent points in a vector space of dimension n plus 1. So therefore, V0 up to Vn are a basis for big V. And we can now write the last point, Vn plus 1, uniquely as a linear combination of these basis elements. Let's write it as lambda 0 V0 plus dot 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 plus lambda n Vn. And this is true for some, in fact, unique lambda 0 to lambda n in our field F. All right, so let's suppose, for a contradiction, that any of these lambda j's are 0. So then we have a relation, linear relation, connecting v0, v1 to vj minus 1, vj plus 1, up to vn and vn plus 1. These n plus 1 out of the n plus 2 vectors, missing out the vj, are linearly dependent, because this equation here doesn't include vj, because lambda j is 0. It's a non-trivial linear relation between them. And that's a contradiction, because of the definition of general position. So, therefore, the lambda j are non-zero for all j is 0 up to n. Now, we chose these representative vectors for the pj's arbitrarily. They're natural up to rescaling by non-zero numbers. So we're free to change them. So let's replace vj by lambda j vj, for j is 0 up to n, but we leave vn plus 1 as it is. And those are just as good representative vectors. So then we have representative vectors v0 up to vn plus 1 for p0 up to pn plus 1, satisfying that equation, but now we've replaced that by v0 and so on. So vn plus 1 is a v0 plus dot 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 plus a vn. Okay, so we found representatives which satisfy a nice equation, and it's rather like the proof of Desargues' theorem when we chose representatives for our points satisfying some nice equations, and that had a little consequence. Okay, so similarly, we do the same thing in W. We can choose representatives W0 up to Wn plus 1 in W for the points Q0 up to Qn plus 1 in P of W. We can choose these to satisfy Wn plus 1 is W0 plus dot 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 plus Wn. All right, so now we're going to construct our projective transformation from P of V to P of W, taking the pj's to the qj's. We do this by, well, since v0 up to vn and w0 up to wn are bases for v and w, there is a unique linear transformation in fact, an isomorphism, big T, going from V into W, with T of Vj is Wj, for j is 0 up to n. But actually that equation is good also for j as n plus 1, because T of Vn plus 1 is T of the V0 plus dot 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 plus Vn, which is T of V0 plus up to T of Vn. So that's W0 plus dot 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 plus Wn. And then this is Wn plus 1 by this equation we chose WHJs to satisfy. So now the t of Vj is Wj. From j is 0, not just up to n, but all the way up to n plus 1. All right, now t is an invertible linear transformation. It defines a projective transformation. So let tor going from P of V into P of W be the induced projective transformation. So then tor of Pj equals Qj, where j is 0 up to n plus 1. So that's what we had to prove. So that's proved existence. We also want to prove uniqueness. So to prove the uniqueness, okay, so now for uniqueness, let's suppose that some sigma going from P of V into P of W is projective with sigma of Pj is Qj, for j is 0 up to n plus 1. So we need to prove that sigma is tor. So as usual, we lift up to the vector space. So let sigma be induced by some invertible linear transformation, big S, going from V into W. So then, for S of Vj, it may not be Wj, but because sigma of Pj is Qj, we know that S of Vj is proportional to Wj. So it's some lambda j times Wj, for j is 0 up to n plus 1, and lambda j in the field take away 0. Not the same as the previous lambda j's. Okay, so now, well, let's start with lambda n plus 1 times w0 plus dot 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 plus wn. This is equal to lambda n plus 1 times wn plus 1, because wn plus 1 is that sum. This is S of Vn plus 1 by this equation here for n plus 1. This is S of V0 plus Vn. Then we use linearity, that's S of V0 plus up to plus S of Vn. And this is now lambda 0 W0 plus dot 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 plus lambda n Wn. So we've got two equations here. We can compare coefficients of the Wj's. So as W0 up to Wn is a basis for W, when you have two expressions, the coefficients which are equal, the coefficients of the basis vectors are the same. So you have that lambda j is lambda n plus 1, for j is 0 up to n. So all the lambda j's are lambda n plus 1s. So hence S is lambda n plus 1 times t, because S and lambda n plus 1 t do the same thing to each basis vector v0 up to vn. And proportional linear transformations induce the same projective transformation. So sigma equals tor, and tor is unique. So that proves the second part of the theorem, the uniqueness. And finishes the proof. Okay. Any questions about that? Okay, so as I said, a set of points in general position in a projective space is rather similar to a basis for a vector space. Right, let's look at an example. So for a projective line, a set of points in general position is just a set of three distinct points. So let's consider P0, P1 and P2 and Q0, Q1 and Q2. If these are triples of distinct points, in the complex projective line, CP1, then there is a unique projective transformation, which is the same as a Mobius transformation for CP1. Projective transformation Tor going from CP1 into CP1 with Tor of Pj is Qj, for j is 0 and 1 and 2. So let's find such Tor with, let's say Tor applied to 1, 0 is 1, I, and Tor applied to 0, 1 is 1 minus I, and Tor applied to the point 1, 1 is 1, 1. So two sets of fairly random points. So let Tor be induced by a matrix T, which we'll write as A, B, C, D. Okay, so let's see what equations we need. Well, we need to solve T applied to 1, 0. So A, C is T applied to 1, 0 is, well, 1 I. But it only has to be proportional to that, so let's put a constant lambda 0 in. And B, D is T applied to 0, 1 is lambda 1 times 1 minus I. And finally, well, T of 1, 1 has to be lambda 2 times 1, 1. So that is T of 1, 0 plus T of 0, 1. So let's write this as lambda 0 times 1 I plus lambda 1 times 1 minus I. So that now gives us two equations and three variables, lambda 0, lambda 1, lambda 2. So the lambda j's are all non-zero, and we don't care about a global rescaling. So we're free to fix any one of them to be some non-zero number. So let's choose lambda 0 is 1. These then become two linear plus constant equations, so lambda 1 and lambda 2. You can solve to get lambda 1 is I, and lambda 2 is 1 plus I. And then out of that, you get T is a matrix 1, I, 1. And any non-zero multiple of that matrix will also do to define your projective transformation. Okay, one other comment on points in general position, which is that your favourite set, or my favourite set, of points in general position in CPN is, or RPN or whatever, well, I take 1, 0, 0, and then 0, 1, 0, 0, all the way up to the last one. And that's not quite enough. That's n plus 1 points, but we want an n plus second. And so let's take the last one to be 1, 1, all the way up to 1. And that's about as nice as you can arrange them to be. All right, so that finishes what we have to say about projective geometry for now, although we're going to be using it for the rest of the course. Now we're going to actually go on to talk about algebraic curves. So we're going to start by defining them, and then we'll see what happens then. So, section 2 is about plane curves. Plane curves meaning curves in the affine plane C2 or the projective plane CP2. So let's make the definitions. Affine and projective curves. So, let's start by defining an algebraic curve in C2. Of course, the definition we give will work for other fields, but later on I'll explain why we want our field to be at least algebraically closed, or the theory is going to be fairly badly behaved for reasons I'll explain. So we prefer talking about curves over C than curves over R, because the field R is not algebraically closed. But I'll explain that later. So an algebraic curve in C2 is a subset C of C2, set of pairs x and y in C2, for which p of x, y is non-zero. For p of x, y, some non-zero polynomial of the complex numbers. So in other words, we can take p of x, y to be the sum over j and k greater than or equal to 0, with j plus k less than or equal to some degree, d, of ajk times x to the j, y to the k. And let's take ajk non-zero for some j and k with j plus k equals d. If that's not true, we make d smaller until it is true. And d is the degree of P of xy. Sorry? Oh, sorry, you're quite right, yes. That equals 0, thank you. Yep, and let's also require, as an extra condition, that d to be greater than 0. Because if d equals 0, then p is a constant, and you're taking 0 equals 1, so c will be empty. So it turns out, though it's not entirely obvious, that requiring d greater than 0 forces your curve to be non-empty over the complex numbers. So, well, just one simple example. Well, x squared plus y squared equals 1 is equivalent to taking p of xy is x squared plus y squared minus 1. And looking at the zeros of that, so that's essentially the complex circle in C2. So these are sometimes called affine curves, where affine is really to do with c to the n. And we can also work in F2 for F, a field, and to do algebraic geometry kind of properly, we really prefer F to be algebraically closed. Which I will define later. But for now, let's think about the complex numbers. Okay. So incidentally, we could also have defined holomorphic curves by taking the zeros of a holomorphic function of x and y. You know, we could have taken x times e to the y is 1 or something like that. But that would have been not algebraic. So the algebraic here is to do with us taking a polynomial equation rather than some more general analytic equation. All right. Now let's define the CP2 version of this. So we let big P of x and y and z, and I would often use little p's for the C2 version of something, big P for the CP2 version of the same thing. Let this be a complex polynomial. We call big P homogeneous of degree d if P of lambda x, lambda y, lambda z is equal to lambda to the d times P of x and y and z. And that would be true for all lambda and x and y and z in the complex numbers. So we can then write P of x, y, z is the sum over I and j and k greater than 0 of an a, I, j, k times x to the I, y to the j, z to the k. Now the homogeneous condition requires that essentially, we want a, I, j, k, let's say, is equal to 0 unless I plus j plus k equals d. Because if you have some term aij which was non-zero and ij plus j plus k was not d, then this homogeneousness relation would not hold, because you can see that rescaling here is going to give you a lambda to the I plus j plus k in front of this term, and you want the I plus j plus k to be d. So we might as well include that condition in the sum here, I plus j plus k equals d. So an algebraic curve in CP2 is a subset. Well, so I call that one C. For now, I'll call this one C primed. The distinction from that one is a set of all points x and y and z in CP2 such that big P of x and y and z equals 0. And that has to be true for some P, which is a non-zero homogeneous of degree d. And again, I want the degree to be greater than 0, because if d was equal to 0, then P would be a non-zero constant and C prime would be empty. Okay, and well, we can define by the same definition in RP2 or FP2 for F, a field. Although for finite fields, we have to be a bit careful because this condition is not equivalent to that. That is, it's not equivalent to this condition here. And actually, for a finite field, this will be the condition you want, I think. That it's a polynomial with those with only total degree d terms. Okay. So, well, firstly, why do we impose this homogeneousness condition? So we note that for 0 not equal to lambda in the complex numbers, then square brackets x, y, z as a point in CP2 is equal to lambda x, lambda y, lambda z. So therefore, the P of lambda x and lambda y, lambda z is lambda to the d times P of x, y, z. And therefore, that P of lambda x, lambda y, lambda z equals 0 if and only if P of x and y and z is 0. Because lambda is non-zero, so that's a non-zero number. Okay, so the condition that P of x, y, z equals 0 is independent of the choice of representative for the point square brackets x and y and z if big P is homogeneous. And at least over the complex numbers, that's actually an if and only if. So that's why this is a good condition. So if you Okay, so imposing this condition cuts you down from a two-dimensional thing to a one-dimensional thing. And actually this is a closed one-dimensional subset of CP2. If you made this definition with P non-homogeneous, let's say you took P to be x minus 1, then something unexpected would happen. Well, if you write it like that and you say, well, for some x, y, z representative, then P of x, y, z is 0. So if you just took it to be x minus 1, then the C prime you get would be the set of all points x, y, z where x is non-zero, because you can rescale it to give you 1. And you'd actually get something which is open and two-dimensional. So if P is homogeneous, this gives us something which is closed and one-dimensional. If P is not homogeneous, it can give you something which could be open and two-dimensional, which is not a curve not really a curve at all. So being homogeneous is really an essential condition here if we want to get something which looks like a curve in a meaningful sense. Okay, so now let's relate these two definitions. So we're going to care almost entirely about curves in CP2 later on, but for now I want to explain how the two are related, because it shows you that the CP2 thing is a rather nice generalization of affine curves. Okay, so here is how to relate algebraic curves in C2 and in CP2. So let's embed C2 in CP2 by x comma y maps to the point square brackets x comma y comma 1. So you could have put the 1 in the beginning if you want 1 comma x comma y. I've just done it this way round because I like x, y as my coordinates for C2, but I like x, y, z for my coordinates for CP2. If I'd been using numbered coordinates, I probably would have stuck the 1 at the front. There's nothing significant there. So therefore, C2 is a set of points brackets x, y, z in CP2 such that z is non-zero. So if big C primed is a curve in CP2 defined by big P of x, y, z, then the curve big C, which is C primed intersect C2, where C2 is now being regarded as an open subset of CP2 like that. This is a curve in C2 defined by little p of xy is big P of x and y and 1. Okay. So conversely, if big C is a curve in C2 defined by little p of x and y, and let's take p of xy to be of degree d. Actually, so before I leave this screen, let me just note that that's degree d, whereas this is degree less than or equal to d. Because if big P has a factor z, then the degree of little p is less than the degree of big P, because you have a z there which turns into a 1 when you set z equals 1. Okay, I'll tell you why that's interesting in a minute. Okay, C is a curve defined by little p of x, y of degree d. Then we can take big P of x and y and z to be z to the d times little p of x divided by z and y divided by z. So because the total powers of those things are at most d, you get at most of z to the 1 upon z to the d on the bottom. So this is actually a polynomial, because the powers of x and z, y and z are all non-negative. So this is a polynomial, in fact a homogeneous polynomial, in x and y and z of degree d, with big P of x and y and 1 is little p of x and y. Okay. Well, and if big C primed is the curve in CP2 associated to big P, then C is C primed intersect C2. Okay, so we can start with a curve C primed in CP2 and get a curve in C2 by intersecting just with C2. Conversely, we can start with a curve in C2. We can extend it to a curve in CP2 whose intersection with C2 is the original curve. So, in fact, C primed is equal to C union, in some sense, points at infinity, where this is in fact the set of points square brackets x and y and 0, such that big P of x and y and 0 is 0. Okay, another thing you can say is that you replace x to the j, y to the k by x to the j, y to the k, z to the d minus j minus k. Okay, so well, as a topological space, so CP2 is compact, C2 is not, and algebraic curves are closed. They're really closed because they're defined by the vanishing of polynomials, and polynomials are continuous. So algebraic curves in CP2 are compact because they're closed subsets of a compact space. So algebraic curves in C2 are always non-compact. So that's not obvious. That's a consequence of the algebraic closure of CP2, of C. It kind of means we can find points going towards infinity and then you can make sequences which don't converge. Okay, so adding points at infinity to make projective curves actually compactifies them. And being compact is a good property. We like compact things. So this is kind of saying that algebraic curves in CP2 are better than algebraic curves in C2, because the algebraic curves in C2 kind of have something missing. So going from C to C primed and back to C is almost a one-to-one correspondence. So I've told you how to go from C to C prime to C. There's a kind of special case which is that if Z is a factor of P of x, y, z, then all the line to infinity is contained in C primed. And then, so you go from C primed goes to C, which is C primed intersect C2. And then you can go to C double primed, which is the closure of C. And this does not contain all the line to infinity. So if you go from big P to little p to big P double primed, then you'd have P is P double primed times some positive power of Z. So it's a one-to-one correspondence except for projective curve C primed, where P contains the factor Z and C prime contains the entirety of the line to infinity. But other than that, it's basically you can go backwards and forwards between affine and projective curves. So let's look at an easy example. So let's take our curve to be set of C is set of points x and y in C2 such that x squared plus y squared equals 1. So it's a circle if you like, but it might be more helpful to think about it as a bit more like a hyperbola, because this is isomorphic to C take away 0, which is also CP1 take away 2 points. It's an exercise to find an isomorphism between this curve and C take away 0. And if you factor the x plus y squared as x plus iy, x minus iy, you will see how to do it, hopefully. The corresponding projective curve is C primed, which is a set of points x and y and z, and CP2 such that x squared plus y squared minus z squared is 0. So I took the one on the other side with the minus, and then scaled it up with the power of z. And this thing, you can identify it with CP1, though it's not a projective line in CP2. It's not defined by a linear equation, but it's still isomorphic to CP1 as a topological space and as a complex space. Or topologically, it's a compact two-sphere. And it's C together with two extra points, the solutions of this when z equals 0, which are 1, I, 0, and 1, minus I, 0. Those are the solutions of x squared plus y squared equals 0. So you call them points at infinity. So to get that equation, x squared plus y squared is 0, from this equation, you take the terms in the equation of highest degree, so the terms of degree 2, and you just throw away all the rest. So you replace that by x squared plus y squared equals 0. And those are the points you have to add at infinity. Okay, so, well, the projective case is kind of nicer and simpler than the affine case, in that, okay, you don't have to delete points from your nice topological space there. That's a kind of general fact. Okay. Any questions? No? All right, I suggest we take a 5-minute break while I clean the boards, and then we will go on to talk about some facts from algebra and algebraic geometry, which will give us some kind of things to do. Anyone want to ask any questions? No? All right. Okay, let's start again at 12, basically.